Welcome. Today we'll see transient response. Most of the control systems use time as its independent variable, so it is important to analyze the response given by the system for the applied excitation, which is function of time. Analysis of response means to see the variation of output with respect to time. This output behavior with respect to time should be within specified limits to have satisfactory performance of the system. The time response can be defined as the response given by system which is function of the time to the applied excitation is called time response of the control system. In any practical system, the output of the system takes some finite time to reach to its final value. This time varies from system to system and is dependent on different factors. Similarly, the final value of output achieved also depends on different factors like friction, mass, or inertia of moving elements, some non-linearities, etc. For example, consider a simple ammeter as a system. It is connected in a system to measure current of magnitude 5 ampere. Ammeter pointer hence must deflect to show 5 ampere reading on it. So 5 ampere is its ideal value that it must show. Now the pointer will take some finite time to stabilize to indicate some reading, and after stabilizing also it depends upon various factors like friction, pointer inertia, etc. whether it will show accurate 5 ampere or not. Based on above example, we can classify the total output response into 2 points. First is the part of output during time it takes to reach its final value, and second one is the final value attained by the output, which will be near to its desired value of if system is stable and accurate. So successfulness and accuracy of the system depends on the final value reached by the system output, which should be very close to what it is desired from that system. Thus, final state achieved by the output is called as steady state, while the output variations within the time it takes to achieve the steady state is called as transient response of the system. Therefore, this is nothing but transient response of the system. So, transient response can be defined as the output variation during time it takes to achieve its final value. The time required to achieve the final value is called as transient period. It can also be defined as that part of time response which decays to zero after some time as system output reaches to its final value. Transient response must vanish after some time to get the final value closer to the desired value. Such systems in which transient response dies out after some finite time are called as stable systems. Therefore, steady state response can be defined as it is that part of the time response which remains after complete transient response vanishes from the system. That is, response of the system as time approaches infinity, from the time at which transient response completely dies out. The steady state response is the final value achieved by the system output. Generally, mathematically we can have total time response is equal to transient response plus steady state response. Therefore, C of t, total time response, is equal to Ct of t plus Css. The difference between the desired output and actual output of the system is called as steady state error, which is denoted as ESS. This error indicates the accuracy and plays an important role in designing the system. Therefore, this is on y-axis step input is there. This is the horizontal line step input. Now, this is the actual response. This indicates the error. This is known as C. Y-axis is CT, that is step input. Now, this is the transient time. This is the steady state time. Figure A indicates when Ct of t is exponential. Now for figure B, when Ct of t is oscillatory. Again, this is the step input. Now this is the actual response. Oscillatory means fluctuation is there. Minimum, maximum and minimum values are there. Now up to this, the system becomes stable. That's why up to this time is known as transient time, and after this it is known as steady state time. Steady state analysis of unit step input. In practice, many signals are available which are functions of time and can be used as reference inputs for the various control systems. These signals are step, ramp type, square, wave or triangular etc. But while applying these signals for analysis of systems, it is highly impossible to consider each one of it as an input and study the response. Hence, from the analysis point of view, those signals which are most commonly used as reference inputs are called as standard test inputs. The evaluation of the system can be done on the basis of response given by the system to the standard test inputs. Once system behaves satisfactorily to a test input, its time response to actual input is assumed to be up to the mark. One of the standard test signals is step input, which is explained as follows. Now this is the graph. This is the amplitude. This horizontal line up to this is known as step input. X-axis denotes the time. Step input is the sudden application of the input at a specified time, as shown in figure. Sudden application of input. Mathematically, it is described as R of t is equal to A for t greater than equal to 0. R of t is equal to 0 for t less than 0. If A is equal to 1, then it is called as unit step input function and denoted as u of t. Laplace transform of such input is A divided by S. As discussed earlier, steady state is the part of the output which remains after transients completely vanish from the output. Also, the steady state error is the difference between the actual output and the desired output. Now we will see derivation of steady state error. Derivation of steady state error. Let Rs is equal to Laplace transform of R of t. Es is equal to Laplace transform of error E of t. Bs is equal to Laplace transform of feedback signal V of t. Hs is equal to Laplace transform of feedback element. Cs is equal to Laplace transform of output signal C of t. Therefore, from this closed loop control system, now R of S is the input, E of S is input error from R of S and V of S. G of S is feed forward element, H of S is feedback element, C is the output element. Now for negative feedback system, this signal of B of S is negative, that's why this is known as negative feedback system. Negative feedback means what? Output is less than input, that is known as negative feedback. Therefore, from figure you can write Es is equal to Rs minus Bs. Es is equal to Rs minus Bs. but Bs is equal to CSHS. See that Bs is equal to Cs because the value of this signal is Cs into Hs. Therefore, Es is equal to Rs minus CSHS. Also, Cs is equal to what? Es into Gs. Es into Gs. Cs is equal to Es into Gs. Therefore, Es is equal to Rs minus Es into Gs into Hs. Therefore, R of S is equal to Es plus Es Gs Hs. Taking Es common, therefore R of S is equal to Es into bracket 1 plus GHHS. Therefore Es is equal to Rs divided by 1 plus GSHS. If positive feedback is used, then E of S is equal to Rs divided by 1 minus GHHS. For unity feedback system, that is Hs is equal to 1, Es is equal to Rs divided by 1 plus minus Gs. The inverse Laplace transform of Es is denoted by Et, given as Et is equal to L inverse of Es. Now steady state error is indicated by ESS and is given as ESS is equal to limit of t tends to 0, E of t is equal to limit of s tends to infinity, SES, as limit of t tends to infinity of f t is equal to limit of s tends to 0, SFS. Therefore, ESS is equal to limit of s tends to 0, s into Rs divided by 1 plus GHHS. For unit step input, R of t is equal to AT for t is greater than equal to 0, and R of t is equal to 0 for t is less than equal to 0. Therefore, Laplace transform of R of t is given as R of s is equal to Laplace of R of t is equal to A divided by s square, and for unit step input A is equal to 1. Therefore, this is known as transient analysis, and we have studied step input function. Therefore, we will stop here. Thank you very much.